Everyone, welcome to my presentation. My name is Reza Farahani, PhD researcher at University of Klagenfurt, and today I'm pleased to present our recent work entitled LEADER, a collaborative Edge and SDN-Assisted framework for HTTP adaptive video streaming. The agenda of my presentation includes introduction, then I will express our primary motivation for this work, explain different aspects of the proposed solution, talk about the evaluation setup and present experimental result, and finally I will conclude the presentation and give some direction for future work. Video streaming traffic has become the primary type of traffic over the internet, and the statistic shows it includes more than 50% of total video traffic over the internet. HTTP adaptive streaming, or HAS, is one of the predominant technology for video delivery. The strategy behind this technology is dividing the whole video into a small parts called segment, then encode each segment into different resolution or quality called representation, store them our CDN or origin server. So each client can run an adaptation strategy for selecting the best representation based on local parameters like buffer or network connection. Having these local parameters also doesn't have insufficient network information makes pure client-based adaptation decision to imperfect adaptation policy. So network-assisted video streaming for HAS is introduced as a promising technology for solving this problem. In this technology, a network component with a global view of the network is employed to assist video player for making precise adaptation decision. Modern networking paradigms like software-defined networking, network function virtualization, edge computing have been used for designing modern network-assisted framework. As you know, in conventional network architecture, control plane, data plane, and data plane are both located in one network device like switch, also router, any type of network devices. So it makes the network device administration the complex process. Also, it imposes a lot management overhead to the network. For solving this problem, control plane and data plane can be decoupled from each other. Control plane can located in a separated layer or device can called SDN control. So SDN control is considered as a central point of the network and manage all the network with a standard communication interface like OpenFlow here. Also provides programmability feature to the network and is the network management. As another networking technology, NFV is introduced. In NFV, each function of the network like routing, switching can be virtualized, located top of the SDN controller, any node of the network or any node of the network as a virtual network function. So it reduces OPEX, CAPEX costs, accelerate innovation, and has a lot advantages to the network. Another networking paradigm is edge computing. In edge computing, storage, also computation resource are located close to the end user. This feature improves network latency and bandwidth consumption. But as you know, these resources are limited, and it's not just dedicated for video optimization and video optimizing purpose. So incorporating SDN NFV edge computing has a lot advantages for video optimization purpose. The motivation for this work is investigating the answer of this question: how we can use edge resources efficiently to optimize users' QoE and network utilization, how we can design edge and SDN-assisted HTTP adaptive streaming framework. Also, how we can establish a collaboration not only between SDN controller and the edge devices, but also between edge devices for some computation intensive tasks like video transcoding. So the final question are about implementation, how we can implement in a real world, in a larger scale scenarios. Also, how we can have a system without any client-side modification compatible with any type of HAS player. For answering this question, we design Leader. We leverage SDN, NFV, and edge computing paradigms and tries to use some capability provided by SDN controller and edge devices and present this hierarchical architecture. Our architecture includes 3 different layers called edge layer, CDN layer, backbone layer. In edge layer, different edge devices called local edge server and neighbor edge server or NES are located close to base station. For example, G-Node B in 5G literature. All of them are equipped with video transcoding, also partial cache, and are connected via OpenFlow switches to the SDN controller. So they can place as a gateway of the clients, HAS clients, also the SDN controller or top layers. So they can send some information for their computation, available computation, receive requests from the client side, also their cache occupancy to the SDN controller. SDN controller also receive periodically some information about cache occupancy or cache map from the CDN layer and can decide about best location for serving clients' requests via this message. For this purpose, we design an MILP optimization model. We formulate our problem as an optimization model. And we wanted to answer this question: where is the optimal place for serving clients' requests with minimum latency? LES, NES, cache servers, or origin server. Also, we wanted to know what is the optimal approach, transcoding, also fetching, or what is the optimal action based on our design action tree. We can directly serve client requests from partial cache of LES or run transcoding our LES, select best neighbor edge server NES, directly serve client requests, run transcoding over that, or send the higher quality to LES, run transcoding over LES, or using origin server, CDN server directly, or again fetch the higher quality from CDN server and run transcoding over LES server. For this purpose, the objective of our optimization model is just for minimizing the client serving time, including fetching plus transcoding. Also, we consider 4 groups of constraint called action selection constraint, serving time constraint, considering some resource consumption like bandwidth, like transcoding our edge devices, and force CDN and origin server to don't use the transcoding capability. But as you know, this optimization model has a lot time complexity. For remedy this problem, we use lightweight heuristic approach. Also, we consider a bandwidth allocation strategy to investigate its impact on improving QoE, also network utilization. For this purpose, we use a time-slotted fashion as depicted in this figure. In the first part, each edge devices are updated by the SDN controller in edge update interval. Then each edge devices can serve clients request per client request in the second interval. So the SDN controller run these lightweight heuristic algorithms in a separated thread to first select best path run the bandwidth allocation strategy, then passing some required mentioned information to each edge devices. And edge devices can separately decide about the location of the best server for fetching or running transcoding based on the action tree and finding optimal action. But let's talk about our bandwidth allocation strategy. As depicted in this simple topology, there are a lot common or shared links between the selected paths by the SDN controller. We wanted to know the amount of allocated bandwidth for each edge devices connected to other edge servers. By our introduced policy existed in the paper, we could assign and allocate an appropriate value of bandwidth to each edge devices based on their hop count, also their passes. As you can see, it's listed here in allocated bandwidth column. In our evaluation setup, we use and design a larger scale cloud-based testbed, including 300 nodes. All of them are run our Zen virtual machine. So our testbed includes 250 clients, 4 cache servers, 40 OpenFlow switches, also floodlight SDN controller, 5 edge devices, a video dataset. You can find more information in the paper. For the evaluation aspect, we evaluate the performance of leader and compare the result with non-edge collaborative baseline system called N-equal and default edge collaborative system called D-equal. In N-equal, we don't use any edge collaboration in SDN-enabled environment, but we have edge devices. In the second one, we just use Edge and SDN-assisted video streaming without any bandwidth strategy. And we compare results with common QoE parameters and network utilization parameters. For example, ASP shows average segment bitrate, AQS average number of quality switches, number of stalls. Also, stalls duration are shown by ANS and ASD respectively. And we use ITUT P1203 as a comprehensive QoE model for average perceived QoE, and we evaluate cache hit ratio, edge transcoding ratio, backhaul traffic load as network utilization metrics. As you can see in this figure, our approach leader could outperform both approaches in terms of ASP and AQS. Also, leader achieve best result in terms of stall duration and stall average number of stalls compared to baseline approaches. Also, we improve the average perceived QoE by P1203 in our approach. Finally, the number of cache hit ratio increased in our approach. Even our approach is a collaborative system because we use the bandwidth allocation strategy. We could improve the result of edge transcoding ratio. Also, we use less bandwidth, backhaul bandwidth compared other approaches. As a conclusion, in this paper, we leverage SDN, NFV, and edge computing and present leader. We design and formulate our problem as an MILP model and introduce lightweight distributed heuristic with bandwidth allocation strategy. We implemented our approach in a larger scale testbed, and the result shows that our approach could outperform baseline approaches in terms of QoE and network utilization by at least 22 and 13% respectively. Extending proposed action tree, also employing learning approach are possible future work direction. Thanks for your consideration. Also, please feel free to contact me if you have any question. Thank you. Goodbye.